Let's work on an example of finding the torque on a loop of current in a magnetic field using the idea of moment of inertia. All right, so let's consider 30 turns of a circular coil of wire of radius 5 centimeters. That coil is lying in the plane of a uniform magnetic field of 1.2 Teslas. And what we want to do is we want to find the torque on the coil and the direction that it's going to rotate. And we're given that the coil of wire carries a current of 5 amperes. So the strategy we're going to use is that because we're trying to find a torque on something that's in a magnetic field, the natural relationship that comes to mind is the fact that we know that the torque on something with a magnetic moment is equal to that magnetic moment crossed with the magnetic field. Remember, we are trying to solve for the torque. We are given the B field, that's the 1.2 Tesla up here. So that just leaves us trying to figure out the magnetic moment of this current loop. Previously, we have defined that the magnetic moment of a loop of current is equal to the amount of current flowing in the wire times the area of the loop. Now, in order to turn this into a vector, we will use the area vector, which, if you recall, is the vector that has a magnitude that is equal to the cross-sectional area and has a direction that points perpendicular to the actual surface of that area. Finally, because our coil consists of multiple loops of wire, we'll multiply by n, where n is the number of loops. In this case, that would be our 30 turns. So we're given the number of turns. We know the current running through the wire, and that just leaves us with the area vector to calculate. Of course, the area for a circle is just pi r squared, where r is the radius of that circle. We're given the radius, that's the 5 centimeters. We know pi, so we now know the area. Putting it all together, we can now calculate the magnitude of the torque to be equal to the magnitude of the magnetic moment vector times the magnitude of the B field times sine of the angle between those two vectors. Plugging in our result over here, that the magnetic moment is just NIA, we can write this as NI times the magnitude of the area vector times the magnitude of the B vector times sine of theta. And finally, substituting in for our equation for the area, we can now write the magnitude of the torque is equal to Ni pi r squared times the magnitude of the B vector times the sine of the angle between the two vectors. This is then our result in terms of known quantities. And if we plug in the numbers here, because we have a known value for n, that's 30 turns, a known value for the current, that's 5 amps. Pi, we know, r is 5 centimeters, B is 1.2 Tesla, and the angle between the magnetic moment, which points straight out of the board because the area of the loop is in the plane of the page, so the perpendicular to that for the area vector points straight up at us out of the page. And the B vector, and I just realized that this drawing lost its arrowheads, is in the plane of the page and pointing to the right. So the angle between them is 90 degrees, sine of 90 is 1, and if we plug in all those numbers, the final answer is 1.42 Newton meters as our final answer for the magnitude of the torque. Next, we need to calculate the direction that the torque will cause the coil to actually rotate. There are two methods we could use here. The first method is to look at the torque vector, which in this case is mu cross b. And to do this, we're going to make use of what I've been calling the magnetic moment right-hand rule. And to apply this, we take our right hand and we curl our fingers in the direction that the current is circulating. And so if our right hand is held, in this case we would hold it upright so that our right hand fingers will curl in this counterclockwise direction, and then your outstretched thumb will point in the direction of the magnetic moment. And in this case, with our hand held properly so that our fingers curl counterclockwise, our thumb points up out of the page. This therefore gives us the direction of the magnetic moment vector. We already know, and again this drawing lost its arrowheads for some reason, that the magnetic field is in the plane of the page pointing to the right. So now we can do the cross product mu cross b. Right? And we do this using the torque right-hand rule, which is similar to the force right-hand rule. You take the first vector, which we just determined points up out of the page, and you align your fingers of the right hand straight up along that direction. And then you have to orient your hand so that when you start to close your hand, you will push, using your fingertips, the mu vector into the direction of the b vector. Right, so in this case, that would have your fingers pointing initially up out of the page, with your pinky kind of oriented so it's towards the bottom of the sheet. And as you push that over into the direction of the B field, your outstretched thumb should point straight upward. And let's pick a color for that. Let's make that purple for today. So that your torque will end up pointing this way. Then, once you know the torque direction, you just have to remember one more thing, which is that when you've determined the torque, it points in a weird direction. But from 1A, you'll hopefully remember that if you orient your thumb to point along the torque direction, then your right hand fingers will indicate the direction of rotation associated with that torque. In this case, with your thumb pointing up towards the top of the page, your right fingers will cause the rotation such that it's into the page on the right side and then swinging around to be out of the page on the left side. So that means it is into the page over here and out of the page over here, and that's how the coil will rotate. Alternatively, you could use a second method in which you forego the torque entirely and use the force right-hand rule on different segments of the coil. Now, the force right-hand rule that's going to be most applicable here is the one that says force is equal to I L vector cross B vector. Right? Because we're given current and we know the B field, we could maybe rewrite this as the force per unit length is equal to I L hat cross B. And we know the L hat direction points in the same direction as the current. So over here on this side, here the L vector points up when you're at this particular point, because that's how the current is moving at that particular point right here. And the B vector we know is pointing to the right. So then if we take the L hat cross the B vector at this particular point and use the right-hand rule, we will get that the force per unit area is pointing into the board, just as we found using our previous method. We could do the same thing over on this left-hand side where the current is pointing downward, so the L vector on this side will point downward. Cross that with the B vector, which is still pointing to the right, and the force right-hand rule will again tell us that the force will then point up out of the page. Over here we had the force pointing into the page, right? And therefore that will give us the direction of the rotation that's consistent with method 1. You can confirm for yourself that if you take the portions of the coil that are down here, they point to the right, which is parallel to the B field. And because sine of 0 we've written phi to be the angle between the L vector and the B vector. And down here, that angle is 0 degrees. Sine of 0 is 0. And so this little bottom portion right here does not feel a force. And so it just spins around. And so we would call this direction counterclockwise when viewed from the top of the page. And that's it.